So in our final video on energy, we're going to have a look at what happens if we actually can't ignore friction and air resistance. And this is where energy becomes a superior way of dealing with these questions to SUVAT. And we're going to have a look at, say, the track not frictionless. Thomas returns to being our runaway train and again falls through a change in height, delta H. Now, what we're going to do is say the track's not frictionless. So it's like we did in the previous video, it's extending the equation to account for this friction factor. So over here we've got half mu squared and he's raised, so he's got a factor of mg delta h. And over this side what we'll have is he will reach a speed of, or a kinetic energy rather, of half mv squared at a speed of v. But because there's friction involved, he will have travelled a distance s along the track, and the frictional force will be F, multiply that to the distance S, and we've got an extra factor in the equation, the work done by the friction. And those two things should be equal, but we've now got this additional factor that we didn't have in there in the previous one. If you know the length of track that he's travelled through, and you know the speeds, we know the change in height, we can then find out this frictional force, how much friction there is on the track. Now, quite simply, we know that all the energy is still transferred, but we know now that we're losing some to friction as heat. And what that means is that we've effectively lost some useful energy from the system. And the proportion that we lose, or the proportion that's useful rather, is known as the efficiency. Efficiency is given a Greek symbol eta, and it's simply given by the useful work done divided by the total energy input. What we would do in this case, we would say the total, the useful work done would be half mv squared, the total energy input would be all of this term, divide them through. You may wish to times it by 100 to turn it into a percentage, to find out what percentage of the total input actually came out as kinetic energy at the end. And it gives you an idea of how much was lost as friction along the way. What's important here is to not get the idea too much into your head that friction's a terrible thing. It can be a bit awkward for certain situations and certainly prevents things getting too quick, but also it's vital to all mechanical systems as well. Without friction, Thomas wouldn't come to a stop and he might run away forever. Nobody would want that. There'd be a lot of children across the world crying if Thomas disappeared off the end of the track somewhere into the Irish Sea. But also, if you think about just getting Thomas moving in the first place, assuming that he's not a runaway train, we've got to think about, well, if he's sat on the track and there's no friction, there's no grip between his wheels and the track, all his wheels will do is spin on the track and the train will never even begin to move. So friction sometimes, is the enemy of movement. Sometimes it's there acting against it, trying to slow things down. But without it, we'd never get going. And when we got going, we'd never stop either. A further aspect of efficiency would just be to consider the power that goes in and out of a system. So we look at the equation again, useful work done. We know that the power there would be useful work done divided by time. That would be the power output, the useful power output. And we've got total input energy on the bottom of the equation, and that would be the total input energy divided by time in terms of power. The time in both those situations is obviously the same, so we can also consider efficiency to be the useful power output divided by the total power input. So the equation works both for energy and for power, so whether we're working in joules or watts, we get the same equation as long as we're consistent with those units.